Normally, when I see all of these words together in the title of an article, I'm thinking, oh, it's clickbait, or oh, they're trying to sell me something. But this is one of the rare instances where that is not the case. Today, we're talking about a new RCE vulnerability in Apple AirPlay, and it probably is going to be the biggest bug of the year. In this video, I want to break down the nature of the bug, talk about what the bug is, how something like this can exist, how you can mitigate it, and if Rust would have solved this bug. Now, the team over at Oligo Security Research has discovered a set of vulnerabilities in the Apple AirPlay protocol. They discovered like literally, I think, over 20 bugs in the Apple AirPlay protocol, but what's crazy about them is it led to this thing called zero-click RCE. If you don't know what zero-click RCE is the ability for a local attacker to get code execution on your device, right? RCE being remote code execution. Zero click means you don't have to do anything for the attacker to get into your system. Just by existing and them interacting with you, they get code execution on your computer and are able to use that code execution to install malware. What's crazy is this is a bug not only in the Apple AirPlay protocol, so it affects Apple products. This is also a bug in the AirPlay SDK, the software development kit, which means any device that implements the SDK that an attacker can interact with the AirPlay protocol is vulnerable to one of these bugs. There are two primary bugs we're going to talk about. The first bug here affects macOS. This is the zero-click RCE, the one that's very scary if you have a Mac product that you're using actively right now. This is CVE 2025-24252. This bug is a use after free vulnerability. Use after frees are this really interesting thing in software where in memory, when you're writing code for systems level languages, you have to allocate memory from the kernel to do some kind of operation, right? That's called the heap. People use that word interchangeably. When you are done using that heap memory, give it back to the heap, and it is now being considered freed. The issue here is if you still have a pointer to that free memory, you're able to use it after it has been freed. The memory is free, it's been given back to the heap, but you actually still are able to touch it. It is still mapped into your process's memory space. What this can lead to is a thing called a type confusion. If you have two separate pointers that are pointing to the same chunk of memory where one is thought to be freed and the other is not freed, in many scenarios, the type that the compiler is using to point to those two chunks of memory are different types. So in the runtime of your program, you can treat the same block of memory as two different types. And what this can give you is a write, what, where primitive. By using a use after free into type confusion, you can use a write, what, where, a www, that gives you the opportunity to write any piece of data to any location in the memory map of the process. This example in C, I think, captures it very well. We have two structures, cat and dog. Notice that both of them have a pointer, but the pointers are in different slots in the struct. If I were able to set the age of a cat and then get the compiler to think that that structure is actually a dog, I'm able to set the value of the bones pointer. And then if ever there is a use of that bones pointer to set the number of bones the dog has, I know this example is very contrived, but we're able to arbitrarily write that bones value to whatever value we set in the age. This is a write, what, where via type confusion. Now, knowing where to write things requires you to have some kind of memory leak where you can bypass ASLR, but if you're given a write, what, where in a process, most of the time you also have a bug somewhere else where you can leak information to write data to a location. Either that or the binary you're attacking doesn't get randomized by ASLR and you can write data to a location. This allows you to overwrite things like vtable entries, global offset table overwrites in the Linux environment, and a variety of other attack methods. And by doing this, this allows the attacker to get remote code execution on their remote device just by being able to talk to the AirPlay port, which by the way is port TCP 7000. Insane. Now remember, this is a bug not only in macOS, the Apple implementation of AirPlay for the Mac, but also the AirPlay SDK. Remember, the whole point of AirPlay is that an Apple device can push music, video, etc. to other devices, one of them being speakers and receivers. Now, the people that manufacture speakers and receivers are not going to implement AirPlay manually. That'd be ridiculous. So what Apple does is they publish an SDK, a software development kit that allows the manufacturer of the speaker to have an easy API that interacts with the devices, and they implement the back end of that to talk to their proprietary hardware or protocols. Now, the crazy part about a bug being in an SDK means that every implementation that uses this SDK is vulnerable to this attack. And this is kind of crazy in 2025, especially coming from Apple, a stack-based buffer overflow that gives people a zero-click RCE that can run anywhere. And in this video here, I'm not gonna watch the whole thing, but they actually get code execution on a speaker. I'll wait for this to go away. Oh, hello, Theo. Basically throw the exploit at the speaker. They use a ROP chain, a return-oriented programming chain, and then just use that to call out a bind shell, and they can just netcat into the speaker and their root, right? So fucking insane exploit. But the key word here is the word wormable. Wormable is where it gets pretty scary. A wormable exploit is an exploit where if a hacker exploits onto a device using this vulnerability, they are able to use that device as a pivot point to worm to other devices that device sees. Consider this example. You get your iPhone hacked on a local network. Remember, these vulnerabilities are required for you to be on the same Wi-Fi network as the attacker. They install malware on your device, and then when you go home to your home network somewhere different than where you currently are, they are now able to throw from that malware the same exploit onto other devices that are on your network as well. And then from there, those devices go somewhere else. It's literally like a human virus or like a biological virus where when the person goes into another place, they are spreading it to new people, those people are infected, and then they go somewhere else, etc., etc. It is literally a virus in like the most natural sense of the term. And even more concerning is the ability for an attacker to compromise a speaker, for example. The speaker can now be used as a C2 place or a place for malware to live for a wormable network of attackers, right? And then the speaker can wait for other iPhones to appear. They can throw the iPhone version of the exploit, and then that is now compromised, and that also is used to spread the worm. So I think it's very reasonable that Apple and Oligo are not spreading the proof of concept around to throw this exploit, because for a few reasons. One, the script that they ran on the Mac itself did not seem extremely complicated. Like, obviously it's not easy what they're doing here, but it doesn't seem like there's a lot of back and forth going on. So it probably isn't super complicated. That's terrifying. Hello, Caleb Hammer. The RCE on the speaker is literally a buffer overflow, like baby's first exploit type of stuff. Now, obviously, it's not fair to talk about exploits if we don't talk about mitigation and remediation. If you are using an Apple device, go and update that device. Now, if you have a device that is vulnerable to this attack because of the SDK issue, every manufacturer has to put out a patch to those devices that contains a new version of the SDK, so like there's literally no way to answer when that would happen, but I think a patch is available right now to mitigate the risk of this bug. If you don't have time to patch or can't patch or whatever, just also disable the AirPlay receiver functionality, which basically means that you're not allowing traffic into your computer to act as an AirPlay receiver. And then if there's some network-wide issue where you're concerned about devices talking to each other over AirPlay, just watch out for traffic over port 7000 TCP on Apple devices, which is the port that is used for AirPlay. Now, the question you've all been waiting for the answer for: would Rust have fixed this vulnerability? Actually, yes. So a use after free and a stack-based buffer overflow are like two of the primary things that Rust is designed at mitigating. So one is a spatial vulnerability, spatial being the space of memory. A buffer overflow is where you have a buffer and you are able to leave the buffer into space around it, right? A spatial memory safety violation. And the other one, a use after free, is a temporal memory violation. There is a time or a statefulness associated with that memory, and once it's freed, that label should no longer be able to use that data, but it's able to use it in a state that it should not be able to use it. So there's actually two different kinds of violations that Rust is literally designed to fix. So would Rust have fixed this? Yes. Anyway, guys, that's it for now. Thanks for watching. I love doing these little exploit breakdowns. I have a lot of fun with these. If you like them, do me a favor, let me know in the comments down below. Also, hit subscribe while you're at it, and then go check out this video about a PS4 exploit that was pretty cool. Not as dangerous as this one, but also pretty awesome. We'll see you over there.